All right, any questions about logistics or anything we've covered so far? Right, 2 items are due per week on a Monday. How many are turning in your 2 items per week, the readings and all that? Okay, I'm only seeing 2/3 of the hands, so I hope the rest of you are doing it too. But 2 things are due every week, Monday, as described on the class website, so please do that. Continuing with the historical arc, last time we talked about Aristotle and Plato, and now we're going into Archimedes. He was a mathematician, a physicist, again, 200 BC, a long time ago, but the leading scientist of that classical antiquity era. He basically pioneered hydrostatics, mechanics, so early physics, basically. Invented the principle of lever and the spiral. The Archimedes spiral can lift things up an incline. And he basically originated the concept of infinitesimals, arbitrarily small quantities, taking as limits. And so that predated calculus by a good 1,500 years, a millennia and a half. So Newton based his work on Archimedes' notion of infinitesimals. He also approximated pi to a great many digits, invented various mechanisms and devices, including naval weapons and siege weapons, and very importantly, invented a large number notation. We'll talk more about that later, but it's very important to have a good number notation to allow you to count, to do arithmetic. I know it doesn't sound like much, but if you can't count well and do arithmetic easily, you can't do math very easily. And if you can't do math very easily, you can't do engineering on top of math and science on top of math, and it hobbles, it stifles your entire technological development. You know, think about that. Right? I mean, try to take the square root of MVXXVICCIX, or whatever the Roman numeral is I just mentioned. It's very unwieldy. Roman number notation is not very good. It just stifles the mathematics. It tries to sit on top of that, which in turn stifles the science that sits on top of that, and the engineering that sits on top of the science. So, very important to have a good number notation, like a decimal notation, base notation. Anyway. He gets a lot of credit for doing his stuff, and even today we use all of his principles. The principle of lever, Archimedes spirals is an example of that in lots of places. There's even industrial string spirals, Archimedes spirals, that are used to pump water up an incline, and as the water goes down the incline at other times, it reverses the motor into a generator. It actually generates electricity, so it helps control floods. Sadly, he was killed during one of the sieges. He was considered to be a very strategic asset, him, the person. And all the soldiers had standing orders not to kill him during the many sieges of ancient Greece. And sadly, one of the soldiers didn't recognize him and killed him. And that was a very big mistake. Whoever he was helping had the upper hand. This is his crater, named after him on the moon, as seen through the Apollo lunar mission. If only he could have seen that. That's that spiral I mentioned earlier with its principles of operation. So a lot of later science and engineering was based on his stuff. He also pioneered and correctly stated the principle of buoyancy. What's the principle of buoyancy? Why do things float? He's the first in history to explain that. Certain things you put in water, they sink, others, they float. And not just water, any liquid, really. Why? Yeah. Okay, so is it about density? So why is a ship floating? Because it's made of metal, right? The hull is made of steel, and steel is denser than water, right? So why does a ship float then? It's not obvious, is it? He's the first person that got it right. Yeah. Yeah, you displace something based on your volume. So a ship is made of steel, but it's not a solid steel object. If it was, it would sink like a rock. But rather, it displaces a much larger volume of water based on the volume of the hull, which is much larger than just the steel that's making up the thin layer of the hull. And it displaces a lot of volume. So an object loses from its weight as much as the water corresponding to the volume that it displaces. And if that's more than its weight, it rises. If it's less, it sinks. Anyway, think about that. You can look it up, but he's the first to discover that, and it was no small feat. He also invented puzzles like this one. It's a square dissected into triangles, such that all the areas are perfect integers. And it's very hard to put this back together once you take it apart. It's kind of an early Rubik's Cube type puzzle from Greek times. Here's a t-shirt that says Archimedes is my homeboy. That was cool. Your mileage may vary, but things that I think funny may sometimes you may not agree. So there's his moon crater. There's even a project today called Eureka, which is the phrase he famously said when he discovered that principle of buoyancy. And this project is ongoing today, still tries to figure out everything else that he invented. And we keep discovering new things that he invented that we didn't know about that he invented back in 200 BC. So this project is still trying to look through old manuscripts and sometimes even look at them through using X-rays and tomography, because sometimes they would rewrite on an old manuscript a new one because paper or parchment, more precisely, was expensive. So they would reuse the same parchment over and over again, and many manuscripts were lost, except that using X-rays, we sort of see right through the layers and read old manuscripts that we didn't even know existed because they're sitting right below these other manuscripts that are more obvious because they're the top layer in some museum exhibit. But if you look at an X-ray or some other spectra, you discover new things, and that's part of it. Eratosthenes, around the same time, 200 BC, basically was the chief librarian at the Library of Alexandria. So the Library of Alexandria in 200 BC was sort of the Google of the day. It had manuscripts of almost every treatise that was ever written up to that point. Now, remember, they were writing on stone tablets with chisels. They were writing on parchments. It was very hard to make a copy of a manuscript. You have to be extremely wealthy to even afford to be able to hire the people who will make just a copy of a book, never mind write the book originally. So people didn't have access to books. But that Library of Alexandria, the soldiers around it had standing orders to raid all the ships that come in and look at old manuscripts and confiscate any manuscripts they didn't already have and add it to the collection. So it was kind of a forced contribution to the library, but still the library grew, and it was like the main source of information on the planet, basically, and Eratosthenes was a librarian there. Later it was destroyed by invading armies, sadly, and that set humanity back many centuries, because there was only one copy of many of his manuscripts, so a lot of knowledge was lost when the Library of Alexandria was ransacked by invaders, sadly. He measured the circumference of the Earth to within 1% error back in 200 BC. We didn't have telescopes or airplanes or anything like that, and he got it very, very correctly using basically trigonometry, which means he knew the Earth was round, incidentally. Otherwise, he wouldn't be talking about a circumference. That knowledge, too, was lost. And centuries later, people still thought the Earth was flat. They reverted, sadly. And he calculated the distance from the sun to the Earth very, very accurately, again, using basically primitive trigonometry. He invented the concept of latitude and longitude. Before that, people couldn't even explain where things are on the map. In fact, there were not a lot of maps. They would just say, ride this way for 3 days on horseback, and then go north another 1 day on foot, and then you'll be there, whether it was a city or something. But he said, let's have latitude and longitude, and using these coordinates, it's much easier to explain position and distances and so on. Again, I know it sounds obvious right now. Right? Your iPhone, your smartphone can do all that with GPS. But 200 BC, that was a huge advance. He basically studied prime numbers. He basically invented the earliest known algorithm to humanity, and that was the sieve of Eratosthenes, so-called, to list out prime numbers. And he invented the chronology of ancient history. Basically, it just means writing things down. Whatever happened, you write it down. I know it sounds simplistic, right? What else would you do but record what happens? But up to that point, nobody did that systematically. Even major things like battles and conquests and invasions, people said, oh, it's too bad, but nobody would bother recording it systematically. There's no notion of history. There was some folklore and a few ancient manuscripts floating around and so on. The New Testament hasn't been written yet for 200 years. And so people kind of had a very nearly-willy approach to remembering what happened. And after a generation or 2 or 3 passed, people just forgot because none of it was recorded. So he came up with this cool idea of whatever happens, write it down for future generations. Now we call that the field of history. Right? I know it sounds straightforward, but somebody has had to come up with it, and this is the guy. So Due to him, we know more what happened than less back in ancient times. Of course, we know very little still what happened back then. Entire nations rose and fell that we don't even know about. And we know about the classical ones, the Greeks, the Romans, the Babylonians, but there were dozens of others that nobody bothered to record or write down, and so those are lost, sadly, including their languages and culture. So that's a shame. Now we live in an era where everything is recorded, for better or worse. What you had for lunch on any given day is either on Facebook or on the cloud, or see photos, and there's trillions of cat pictures everywhere and doing tricks, and so in 100 years maybe they'll probably know more than they want to know about this era. But in ancient times that wasn't the case. And he studied everything else too, astronomy, geography, and here's a sieve of Eratosthenes animated. So this is an algorithm basically that eliminates all multiples of 2 in blue, then it eliminates all multiples of 3 in green, and all multiples of the next remaining number, which is 5, in red, and so on. And once you do all that, whatever remains is a prime number. And that's one way to compute prime numbers, many other ways. And that's probably the earliest algorithm known to humanity, due to him. Here's how he calculated the distance around the Earth. He waited until the sun was overhead in some city called Sine, or Sine. And the way he did that is, but it was over the well, and you could see the bottom of the well with the sun reflected the water of the well, so that means the sun is precisely overhead. At the same time, he had somebody else measure the angle of the shadow of an obelisk in Alexandria, a different city, and knowing the distance between the two, right, and knowing the angle of the shadow, which is alpha, it's the same angle in the center of the Earth. So that angle of the center of the Earth, which is the same angle as this shadow of the obelisk, represents this distance L. And once you do that, you can divide this angle into 360 and give it the same proportion as L to the circumference of the entire Earth. And that's how you calculate this. How many get that? Now, it's pretty straightforward now that we explain it like that. But in ancient times, this was brilliant. This was monumental. Even though nobody has ever went to the other side of the Earth, and America has been discovered for a good 15 centuries still, since 200 BC. But still, he was able to calculate the distance. So he has a huge impact crater named after him on the moon, and very well deserved. Speaking of the ancient Greeks, I think I mentioned this before, but I'll say it again, the Antikythera, it's an ancient computer. Just discovered a few years ago, 10 or 15 years ago. And this computer was mechanical, and it was built around 150 BC, which is amazing, right? If you ask your friends or even experts, when was the earliest known computer they can think of, they'll say, Babbage's analytical engine, 1800s. Pascal had a handheld calculator, we'll get to that, 1700s. No, the Greeks had one 2,000 years before that, and we just discovered it. Imagine what else they may have had that we still don't know about. Right? We could have had iPhones 1,000 years ago, if we kept up this pace of invention. We could have cured cancer by now, many centuries ago. There's reasons why humanity kind of got stifled in many times for centuries on end. Let's just hope that doesn't continue very much. Progress will keep up the pace, although it's not guaranteed. Here's very sophisticated computed eclipses, astronomical orbits, and positions and periods of moons and suns and planets, and very, very sophisticated. Had dozens of gears. It was like a Swiss watch, basically. 200 BC. Right? Swiss watches wouldn't have been invented for another, 17, 18 centuries after this in the West. So it even had a manual attached to it, probably chiseled in stone, but that's okay. It's still a manual. And they're still researching this thing, trying to understand all its capabilities and how it was designed. And these are models, modern remakes of it. The original's kind of fossilized. It's just completely rusted out. And, so here are the fossil pieces. And some of them were observed using X-rays and other tomography techniques. But this is what it would have looked like if it was brand new. And it's really quite amazing. So there's an article on the class website. This is one of the required readings. Look at this. We had a computer over 2,000 years ago. We should have kept going. But still, here we are. And we're not doing too badly. We just wasted a lot of time as a species. All right. fast forwarding about 1,000 years, because not a whole lot happened in those 1,000 years, technologically speaking. A whole lot did happen, of not of a good kind, mostly crusades, wars, invasions, holocausts. But this guy, around the year 1000, he was called Abu Ali al-Hassan ibn al-Haytham. How many heard of this guy? In the West, not too many people are aware of this guy, but in other places, he's a hero, and he should be, because he was called the physicist. He wasn't called a physicist, because there was only one on the planet, so it was the physicist. Indefinite article, the was attached to his name. There was only one. And he studied basically everything there was. He was the greatest scientist of the Middle Ages, contributed to every field that existed, including optics and physics, astronomy, anatomy, psychology, philosophy, engineering, and many, many others. And he also pioneered the scientific method, kind of taking up where the Romans, or the Greeks rather, left off, and also pioneered experimental physics. The notion of doing experiments was really popularized and advanced by him even further than the Greeks. And he authored over 200 treatises. Each one was essentially like a PhD thesis, studying new stuff, including optics and many other things. He was Leonardo da Vinci's hero. He was also the hero of Descartes, Galileo, Newton, and Bacon, Kepler, and Einstein. But Leonardo da Vinci was no slouch, right? But this guy was his hero from several centuries earlier. And it tells you so in certain countries, he's on the money. You know, we don't have all dead presidents on the money. We have actual people that are really impressive. You know, contributed to knowledge, to engineering, to science. He had new ideas. You know, advanced humanity forward in big steps. Weren't just administrators of a small region like a president is. So this is the Iraqi dinar with him on there. Other countries pay homage to him similarly. Just to give you an idea of the crazy ideas that he had to combat at the time, there was this notion that the way people see, this was a 1,000-year-old idea, but is that the lights are like, your eyes are like headlights, and they project light onto the objects that you then see. Like car lights, headlights. I know it sounds strange, but that's what people believe, how people can see. Your eyes shine light on things, and they become visible. Which kind of begs the question: why can't people see in the dark then, if your eyes shine light on things? Anyway, but there's many other inconsistencies to that theory, and this etching here actually show you light emanating from people's eyes. So this guy said, no, that's a little silly. Light emanates from other places, hits the objects, and bounces back into your eyes, but your eyes don't generate the light that is necessary. And I know, again, this sounds obvious today, but back then, that was one of the many misconceptions that people had, not even the worst. There was fake news even back then, about how things work and how they don't work. He had to, dispel a lot of that, and he did a good job of it. So he appears on stamps from many countries, not the U.S., sadly. We barely even recognize him in the West, but and there's reasons for that, mostly political. It's pretty amazing, the stuff that he did. Again, around the same era, Leonardo of Pisa, also known as Fibonacci, one of the most talented mathematicians of the Middle Ages. He did a lot of stuff, including the book of calculation, and he invented Fibonacci numbers, but probably his most enduring contribution is not even Fibonacci numbers, but rather positional number systems. The notion that you have digits, and each digit is worth 10 times more than the previous digit, and so on and so on. Like, 1, 100, 1,000, and so on. And that gives you a very succinct, short way of representing very large numbers and manipulating them in a way that enhances arithmetic and mathematics and calculations, on top of which you can build science, and on top of which then you can build engineering, and everything becomes easier. And he didn't even invent that stuff. He basically copied it from the Hindus and the Arabs, which were already using it for centuries. And the Chinese had a good system too. But people in Europe didn't. They were using Roman numerals. And that was pretty sad, because it's very hard to take the square root of this thing, as a Roman numeral, or even figure out what the value is of that thing, much less take square roots of it or sines or cosines of it. So this notion of positional number systems came from the Arabs and the Hindus, and they use slightly different symbols to represent 0 through 9. Some of them were quite similar. Like the Arabic 9 is really the same as our 9, and the Hindu one is similar, and so on. But these are the digits, and from that you can form numbers. Again, I know it sounds obvious, I know it sounds simple, but somebody had to come up with it. And he wasn't even this guy. He just went to this region, saw how they do arithmetic, said, that works a lot better than Roman numerals. He came back, he became very popular, and then science started taking off. Until then, science was very stifled. So there's a Fibonacci Association, there's a Fibonacci Quarterly Journal, the entire journals devoted to his contributions and contributions of his Fibonacci series and Fibonacci numbers and the golden ratio. And the golden ratio is representative in art, in architecture. Basically, it's 1.6 something. It's the square root of 5 plus 1 over 2. It's a very, very interesting number for a number of mathematical reasons. How many heard of the golden ratio? Good. So it appears in structures, as small as flowers or cells, and all the way up to galaxies and very large things. It's kind of a ubiquitous quantity, and even in art and architecture. So Fibonacci also pioneered that, and the golden ratio occurs in lots and lots of places. There's entire books on the golden ratio and on Fibonacci numbers, as there should be, because it's so impactful, and entire fields of study devoted to that. So this is one of the other things they did besides popularizing number notation in Europe. These are Fibonacci spirals or golden spirals. And here are some books on Fibonacci numbers, just a few representative ones. There's many others. Just to show you how ubiquitous those are. And they're even used, Fibonacci numbers and the golden ratio are even used in Wall Street trading. There's securities and stock trading techniques that hinge on Fibonacci numbers and golden ratios and other Fibonacci-like calculations and statistics. Very, very interesting stuff. So here's that book on Fibonacci trading, several books actually, about Wall Street Fibonacci trading. So it's not just a hobby, it's a money-making mechanism as well. Lots of things are built on that. So I'll just leave it at that. Lots and lots of stuff. Doggy T-shirt with a Fibonacci spiral on it. I don't know if it's cute or animal abuse, but your mileage may vary. So René Descartes, 1500s. Again, we have to fast forward a few centuries. Progress was slow during that era of the Middle Ages and the Dark Ages until the Renaissance, and that's why they call it the Renaissance. It was kind of a renewed, enlightened period. Descartes basically invented modern philosophy. He invented Cartesian coordinates. The Cartesian coordinates are named after Descartes from his name. So Cartesian coordinates is a notion that every position in space or in a plane has an x, y, and perhaps a z if it's 3D coordinates. Now, I know it sounds obvious today to say every point has an x, y coordinate. How else would you refer to points, right? On the plane or in space, x, y, z coordinates. But this is the guy who first came up with that notion. Before that, there was no notion of coordinates. So how did people do geometry without coordinates? Remember, Euclid did geometry in 200 BC, 300 BC. And here we're saying this guy invented coordinates almost 2,000 years later. So how did they do geometry 2,000 years before then? Yeah. They used basically axioms that didn't rely on coordinates. They used things like parallel lines and perpendicular lines and similar angles and things like that. The bisected angles and segments, and they did a lot of geometry that didn't rely on coordinates specifically. But coordinates enabled analytic geometry, the study of geometry where now you pay attention to positions, to coordinates, and that's a lot more robust and interesting, and it blew up what you can do in terms of possibilities. He also was very interested in paradoxes and fallacies, and he discovered the principle of momentum conservation, which again seems obvious. You move at a certain speed, and if you try to stop, you keep moving. You can't really stop on a dime. You have inertia. You have momentum. He pioneered that principle in terms of its discovery. I mean, the principle was always there in the universe, but people didn't quantify it, observed it, and gave it the respect that it was due. And Newton then built on top of that when he pioneered Newtonian mechanics. And he famously said, cogito ergo sum, I think, therefore I am. Here it is in French. And basically, there was skepticism of whether we even exist or not. People began to question everything during the Enlightenment period, during the Renaissance. And one of the things they question is whether we actually exist. Because, when you sleep and you dream, you have very vivid dreams. And in your dream, it's hard to distinguish dream from reality. It looks to you like it's the reality while you're dreaming and sleeping. And of course, you wake up and sometimes you realize that was just a dream, and sometimes you make a sigh of relief because the dream wasn't your favorite reality necessarily. And so people wondered, whether all this around us here is one big dream, right? And the movie The Matrix, Neo in The Matrix had this big revelation that this isn't really reality. He started seeing the pixels in it and finally realized that there's something outside it, and this isn't really real. It's just one dream, or in this case, a simulation in The Matrix. How many have seen The Matrix? Very philosophical, interesting movie. Also a very cool movie, but the very deep ideas embedded in it. So, the producers and directors, the writers of it, studied all this stuff as they were writing the script. And people try to prove that this isn't a dream, this reality that we see around us, all of us watching each other and experiencing this common experience, and maybe it's just a shared dream. And then when we wake up, it'll be all different. And so people try to prove that this isn't a dream. And one of the ways that, he thought that the best way to prove it, even though it's very hard to prove, right? When you're dreaming, it's very hard to tell yourself this is only a dream. Think about it. It looks very real. But he said basically, the very notion that we're wondering whether we exist or not is the best proof that we do. Because if we weren't really here, we wouldn't have been able to wonder if we're actually here. So that means I think, therefore I am. I'm able to make cognition about whether I exist, and therefore I do exist. Now, some people don't even accept that as proof, but he thought that's the best you can do given the circumstances. Anyway, so basically that ushered in all of modern philosophy. And he kept pushing on a scientific method, right? He famously said, it's not enough to have a good mind, you must also use it well, and very purposefully, very intentionally and deliberately. So he appears on the money in many places. Again, so this is pre-euro money. This is the French francs, where you have the card there on the money. It appears on stamps in lots of other places. And he well deserves all this respect. You can look at the cartoons offline. He gets his own big moon crater. And that brings us to Fermat. And Fermat was a mathematician slightly after Descartes. And he basically pioneered modern number theory. The Greeks already looked at Diophantine equations and tried to find solutions in integers to certain things, like the Pythagorean theorem. Pythagoras, he was one of the ancient Greeks. But this guy kind of made a systematic study of it. He was also a lawyer and physicist. He looked at analytic geometry. He was a mathematician, but he pioneered the study of prime numbers and perfect numbers very systematically, and discovered the law of refraction, which basically how light passes through lenses or prisms, or even just water. It refracts as opposed to reflects. He does both, of course. And he pioneered many open problems. Famously, he's famous for Fermat's last theorem. Basically, he said that this equation, which is a generalization of the Pythagorean theorem. The Pythagorean theorem says x squared plus y squared is z squared, and there's many solutions to that, like 3, 4, and 5. But if you make the squared cubed, or to the fourth, or to the fifth, or arbitrarily n, as opposed to just 2 in the exponent instead of square, the question was, are there any still solutions to that in integers? There's plenty of solutions are non-integers, but that's not that interesting. But any integer solutions to x to the n plus y to the n is equal to z to the n if n is bigger than 2, 3 or more. And for several centuries, about 350 years, nobody could find out whether that's true or not. It was an open problem for 3.5 centuries until Andrew Wiles in the year roughly 1995, finally, a mathematician from Princeton, finally nailed it and said very unambiguously and proved it that this has no solutions in integers if n is bigger than 2. In other words, only the Pythagorean theorem, when n is 2, has lots of solutions in integers. Anything higher than that in exponent, no solutions whatsoever in integers. So his famous open problem, more than just an open problem that was solved 3.5 centuries later, ushered in entire new fields of mathematics through the work of mathematicians who tried to solve this problem but failed, but instead succeeded in inventing entire other fields of mathematics, including elliptic curve theory and many other fields. So this problem had a huge, giant impact on all of mathematics and therefore on all of humanity through the engineering and science that are built on top of those new mathematical fields instigated by this problem. So it's an interesting way to make a contribution. You state a problem nobody can solve, and thousands of people will try to solve, very smart people will try to solve it over several centuries and fail, but instead will succeed in inventing whole new things besides the original solution to this problem. So this guy got a Fields Medal and very, very impactful problems, many, many books on this problem and how it was solved and all the things that happen in a way to solving it. And it's hard to overstate the impact this problem had on all of humanity and in particular all of mathematics. Here's Andrew Wiles having very good reason to smile as he gave this famous seminar at Princeton, finally solving it. The proof was over 100 pages long. So Fermat, by the way he stated that problem, he put at a margin of one of his manuscripts, x to the n plus y to the n is equal to z to the n when n is bigger than 3. It has no solutions, but I have a small and marvelous proof of this. However, the margin of this manuscript is too narrow to contain my proof, and he just left it at that. And people also wondered whether it was serious or not, whether it was a kind of mathematical practical joke or whether he actually had a proof. Today we think he didn't, because the shortest proof we know is over 100 pages long, and it involves whole new mathematics that were not invented yet in his time. So here's a principle of refraction, and here's a Fermat near triple, and Fermat near miss in one of the Simpsons episodes. It turns out they have mathematicians on staff whose job it is to insert mathematical jokes and mathematical humor into the episodes. You have to really be on your toes to watch those. But this says some number to the 12 plus some other number to the 12 is equal to a third number to the 12. So do you think this equation really is true? Based on what we just said, how many say it can't be true? That's right, because it's not power, the power is not 2, it's not a Pythagorean thing, it's a higher power, so no integer solutions exist because of Andrew Wiles's disproof of Fermat's last theorem. But if you do this calculation, if you compare the left-hand side and the right-hand side, they're almost equal. They're equal to they're equal to within one part in, I don't know, a trillion or something like that. They're very, very close. And this is called a Fermat near miss. Not equal, but almost equal. And there's plenty of those, actually. And there's a whole area as mathematicians study these things to this day. It hasn't stopped. There's even a stage play called Fermat's Last Tango, which is available on DVD or streaming. It's pretty cool, which kind of is a whole play revolving around this problem. You have to be a little bit of a geek to fully appreciate that play. I've seen it. It's great. So it's kind of a musical. And it stars Carl Friedrich Gauss and Pythagoras, of course Pierre Fermat, and Euclid, and of course Sir Isaac Newton. What could be better than that? Your mileage may vary, but I thought it was pretty hilarious and a very fun way to introduce the problem and all of its impact to general audiences. Just saying. All right. Remember we said that problem last time, we said x to the x to the x to the x is equal to 2. And we asked, what's the value of x? Solve for x, this one equation and one unknown. So let's talk a little bit about that now and maybe try to solve it. What do you think x is equal to here? How many have worked on this since last time? Okay, a few of you, good. I'm proud of you. The rest, why not? Work on the extra credit problems for your own good. So anybody want to tackle this? What is x equal to and why? Yeah. Okay, she says x is the square root of 2. How many agree? X is the square root of 2. Why? Somebody else explain why. Yep. Yeah. So when you look at this stack of exponentials and you say, what is this stack equal to? Just the exponent of the first x. Well, the exponent of the first x is just an infinite stack of x's, which is what the original is, including the first x. So if you look at the exponent of the x and the entire thing itself, they're both the same thing, an infinite stack of x's. And that thing is equal to 2. So once you realize that the stack here in red is equal to 2 also, because it's the same as the entire original stack. Just substitute for that stack 2, and you get x squared is equal to 2, and x is plus or minus the square root of 2. Now, if you plug in minus square root of 2, you'll see it won't work. So you stick with the plus square root of 2, and that's what the answer is. And he mentioned titrations very cleverly. There's a general operation called titration, which generalizes power towers, if you will. And this equation, if you set it something other than 2, it converges for values other than square root of 2, and the convergence is between e to the minus e and e to the 1 over e. But don't worry too much about these generalizations, but it has to do with titrations. If you look up on Wikipedia titration, you'll see a whole lot more. And you can generalize to the complex plane. So if x can take complex values, not just real values, it also converges at many places in the complex plane, and it diverges some other places. So this is the complex plane showing convergence of this. Now, I didn't believe that at some point, it's really the square root of 2. How would you experimentally verify it? Well, you can do some calculations. I went to Google Calculator, and I said square root of 2 raised to the square root of 2 raised to the square root of 2. I basically raised square root of 2, for 10 or 20 or 30 times, and just wondered what would the answer be. And sure enough, the answer is 1.998. And if you add more powers of the square root of 2, this number will become 1.9999987, whatever. So it does converge to 2, and this is an experimental confirmation of this. Now, this is not a proof right here, but this better give you answers closer and closer to 2 as you keep throwing in more and more square roots and keep raising them to powers. So always try to experimentally verify what you think is true, just as a double check, just as a confirmation, just as a reality check, right? Both when you do science, engineering, programming, and just everyday life. Always get corroboration from other sources. That's how you can avoid fake news, for example. Corroborate that with other sources. So here we corroborated this with Google, the Google calculator. We didn't have to, but it gives us a warm, fuzzy feeling that Google calculator agrees with our analytic observations that we just mentioned a minute ago. Always try to get confirmation, corroboration from multiple independent sources. It'll keep you out of a lot of trouble in life. All right, so let me give you a few other extra credit problems. We just solved this one, so the bounty on that is off, but here's a bounty on another one. Take a unit square, it's a 1 by 1 square, put 5 points in it anywhere you want, including the boundary, including on the boundary if you'd like, and you can move them around however you want, but when you're done moving them around and they're in fixed locations, doesn't matter where, the question is there always a pair with distance 1 over the square root of 2 or less? In other words, the points can't get too far away from each other if they're going to remain in this bounded 1 by 1 unit square. So first of all, is it always true or not that no matter how you put 5 points in a circle, there's always a pair less than that distance apart, one pair at least, could be more. So first of all, is it true or not? And if it's true or not, prove it one way or the other. Okay, so how many understand this problem? Okay, any questions about this, what the problem states? So I'm putting this for extra credit, think about it, work in groups. How many are working in groups already? All right, when I ask it again next week, I want to see a lot of hands up. It's not too early. In fact, I was hoping that a lot of you will already be working in groups trying to solve these problems, and the problem sets are already been posted to the website first day of class. And so, because remember, I said, it's more than I said, I promised that all the exam questions, most of the exam questions, I don't want to say all, but most of the exam questions, 6 out of 7 exam questions will come straight from those problem sets, verbatim. So you already know what the final midterm would look like right now. There will be subsets of the posted problem, which means to do well on the final and midterm, just solve as many problems as you can. Then if you do, when you come to the exam, just write down all the answers and walk away, because you've already solved them before, and I'm allowing you to work in groups. Any questions about that? So basically, I respect you, I treat you like adults, I give you a lot of freedom and leeway, and I try to treat you in a way that I wish my teachers treated me when I was a student, undergraduate or graduate student way back in the day. So my gift to you, I'm trying to do for you what most teachers didn't do for me. But that means with great power comes great responsibility. So I'm giving you a lot of leeway, a lot of authority, a lot of power, but you need to use it wisely and work along in groups every week. Don't fall behind, solve lots of problems. I'm not going to harass you with daily and weekly deadlines and due dates and deduct points for being late as if you're school children. No, I'm treating you like adults. But you need to do this. And I hope that you use that freedom and responsibility wisely. All right. A similar problem. If there's 5 points in the unit equilateral triangles, it's a 1 by 1 by 1 equilateral triangle. Put 5 points in it however you want. And the question is there always a pair? There exists always a pair, no matter how you put the 5 points in there, including possibly on the boundary, that's okay, with distance less than a half. Again, prove or disprove, and try to do it succinctly. I mean, these proofs are not going to be long. I already mentioned Occam's razor many times. Less is more. Simpler is better. Right? Don't use induction. We already talked about all that. So any problem I give you, you can basically prove in one paragraph, just a few sentences, and sometimes even less than that. So that's already a big hint of what to try, what not to try, where to go, what not to go, what kind of things to avoid. So whenever you start looking at a problem I give you and start looking into trigonometry with sines and cosines and vectors, you're barking up the wrong tree, probably. It's not to say that doing that won't work. It's probably to say that there's simpler ways. Remember the centrifuge problem? There's simpler ways of reasoning and identifying generalities and basic principles that are much better than just raw calculations and point solutions that only work for special cases. So I hope you're kind of getting an appreciation of all that kind of mindset. There's lots of ways to prove things, but some ways are better because they're shorter, more succinct, more generalizable, more elegant, more beautiful than other ways. Right? Aesthetics count now. And it's not just aesthetics. Your intuition will be better off for it. Your ability to generalize will be better off for it. Your ability to solve other problems will be better off for it too. Any questions about this problem? All right. If you put any 10 points in the unit square, what's the maximum pairwise distance? So now you have a lot more points, and so this goes to generalization of the previous ones. And so if you do it in a way that's generalizable and insightful and kind of has Occam's razor written all over it, you'll be able to solve lots and lots more problems of this form. So that's another kind of meta hint of how you should kind of think about these things. All right, Pascal, 1600s, mathematician, physicist, philosopher, studied fluids and vacuums and pressures and physics in general, and basically helped pioneer probability. Why do you think the study of probability first came about? What was the incentive, the motivation for studying probability, do you think? Gambling. Yeah, gambling has been around for a long time, pre-biblical times. People gambled as early as they could talk, basically. And gambling is tricky business. Anybody who's been to Vegas or Macau knows that. Basically never bet against the house. In fact, just don't gamble. It's always rigged in favor of the house. But in order to understand what happens when you gamble, you have to know about likelihoods and probabilities and statistics. And that's what ushered in this study. Of course, now we use statistics for everything. Every field of study uses statistics up and down the field. For doing almost any kind of methodological studies and studies of large numbers and data mining and all that. So statistics have become ubiquitous, but the original motivation was gambling. Pascal has this famous Pascal triangle having to do with binomial coefficients. He invented the hydraulic press, which is basically hydraulics, pistons that are very powerful. Tractors use them, and lots of machinery today use hydraulic pistons using fluid, usually oil, incompressible fluid, to actuate motion and movement and so on. He constructed a mechanical calculator, a handheld mechanical calculator. He sold it, made quite a bit of money on this, actually. And he was very witty, used humor in very insightful ways. And there's a standard international unit of pressure named after him, the Pascal. Whenever you have a unit of measurement of some kind, a standard international unit of physics of measuring any kind of physical phenomena, and it's spelled with a small case letter, not the capital case letter that is associated with the actual person. That's already a very good indicator of contribution and impact on humanity. So Pascal measures pressure. There's a whole bunch of other units like that are named after people that measure other physical quantities. Name some examples besides the Pascal. Watt measures what? Energy or work. Yeah, what else? The Newton measures what? Force. What else? There's dozens of others. Hertz measures frequency, right? Wavelengths. What else? All with small letters, named after the people who pioneered these studies or fields of endeavor. What else? Electricity measured in what? Current, amps, amperes, after Ampere, who pioneered a lot of that. Studies. What else? Coulombs measures what? Charge? What do you say? Angstrom measures tiny little distances, subatomic distances. What else? Faraday's what measures what? Capacitance, right? In fact, a Faraday of capacitance is so large a quantity that we measure capacitors in microfarads and nanofarads and picofarads, actually. It's a very large unit, actually. What else? Yeah. Kelvin measures temperature. Celsius, too, for that matter. Yep. Ohms measures what? Resistance. Good. And there's many others. So just be aware, if you spell it with a small letter, the person who's named after it really did something amazing. And of course, he too is on the money in the French francs before the euro. Of course, now it's just euros. The euros are very plain because everybody had to agree on something, and nobody wanted other people's faces, other countries' people's faces on their money. So euros are kind of a boring currency. But before that, the money in Europe was much more interesting. Here's his handheld calculator. It's got 6 digits, so you can do calculations up to 1 million or so, and each one kind of is meshed with the others using gears inside the box, and he actually produced that, sold it, and something like this was very, very expensive back in the day, and here's the readout. This is the display of the 6 digits with little circles representing numbers, so you can actually do a lot of math using this little box. And if you had to purchase that back in the day, this would probably cost you several years' salary, so it was very expensive, equivalent of the day. So today this would be like, hundreds of thousands of dollars. But it's one of the early calculators. So he gets a lot of respect and homage as a moon crater named after him. There's all sorts of things that depend on these contributions. That brings us to Newton, the big gorilla in the room. Basically invented modern physics, at least Newtonian, what we call now Newtonian mechanics, one of the most influential people in history. So his treatise called Principia Mathematica, 1600s, and pioneered the study of mechanics, Newtonian physics. And this shows you the conservation of momentum principle, animated. How many have seen this little toy like in real life? Good. It's pretty cool. And that's very simple, direct, vivid illustration of conservation of momentum. He also invented calculus as a hobby. We owe him that, for better or worse. If not for him, you wouldn't have to study calculus, but you'll be worse off for it. And he discovered the theory of gravitation, universal gravitation, that gravity basically decreases as an inverse square of the distance and is still proportional to the two masses. Again, that's a brilliant observation. Today it seems a little obvious, but all brilliant things seem obvious in retrospect. That's part of their brilliance, is that they're so simple in retrospect. So now we call it Newtonian mechanics, and sometimes we say Newtonian universe or Newtonian fluid, and many other things are called Newtonian in honor of him because he pioneered that stuff. So basically, he kicked the scientific revolution into high gear in the 1600s, early 1700s. He also invented the reflecting telescope, a telescope with a mirror in it as opposed to a lens. Why would a telescope with a mirror be better than one with a lens, do you think? There's many reasons, but name 7. Or 1. Doesn't have to be 7. Yeah. Yeah, lens will be distortion involved, and also impurities in the glass, and light has to pass through all that and attenuate, and some of the light will be lost to the lens, will be absorbed by it. And so, lenses like binoculars work okay when they're small and thin and you don't have to magnify very much. But if you can use a mirror instead, what other advantages do you think you have besides distortions? Yeah, lens is hard to make, and if the lens gets bigger and bigger and bigger, it becomes more and more opaque to light. If you ever saw a piece of glass that's really thick, it looks green. And if it's even thicker than that, you can't even see through it. So the very width and size of these giant lenses that we would need would be prohibitive, and it would completely occlude the light. And not only that, it'll be very heavy. It'll weigh many tons, and the lens will start distorting under its own weight, actually, which is a problem because it has to be very precisely shaped. Now, if you have a mirror, you can make the mirror out of steel or titanium coated with a reflective surface, and it wouldn't be very heavy, it wouldn't distort very much, and you can make it arbitrarily large. And so this is the guy who invented the notion of using mirrors in telescopes, which allowed us to see the universe like we've never seen it before, including discovering new satellites in the solar system and even new planets. And Galileo's telescope had lenses in it, and it was still pretty good. It was all better than nothing. Don't get me wrong, but this guy enabled us to take astronomy to a whole new level of discoveries. And of course, we already mentioned the Newton, named after him. It's a unit of force. And here's his original treatise, actually his own personal copy, annotated by his own hand. Imagine how much that will fetch on eBay. And here's an early version of his telescope, I think one of his own models, with the mirrors inside. And he pioneered also the study of optics as well. So he gets a lot of credit. He discovered orbits. Orbits are rotations of bodies around other bodies, according to the laws of gravity. So he said if you shoot a cannonball from a mountaintop, if you shoot it with only a little bit of force, it'll plop down pretty close to you. If you shoot it farther, with more force, it'll land farther away and farther away. If you shoot with enough force, laterally, it'll start falling, but it has so much force that by the time it falls, the Earth is curved away from it because it's now so far away because it has so much speed and force that now it'll go orbit. It'll go into orbit around the Earth. And that's what an orbit is. And up until Newton, this relatively simple observation and explanation was unknown by everybody else on the planet except him. And he basically stated it and proved that mathematically this is what happens. And in fact, that's why the moon rotates around the Earth. That's why the Earth rotates around the sun. That's what makes the entire universe work, actually. That's what makes solar systems rotate around the galactic hub. Big revelation to the human race. But the physics are relatively straightforward, inverse square law. So it's one of his many contributions, basically illuminated to us, to the rest of us, how the universe works, gravitationally speaking. And of course, he explains the principle of prism. This is actually a cover from a famous rock album. Anybody recognizes this? Dark Side of the Moon, yeah. Who's the band? Yeah, we used to watch Dark Side of the Moon played in the Lyceum back in the 80s. This was a big deal. To a laser show on the ceiling. It was really cool. Anyway, but I digress. He also quantified mathematically the principle of inertia, and studied elastic and inelastic collisions, and he pioneered Newton's method to basically compute the roots of polynomials or any equations for that matter. Here's a graphic illustration of using Newton's method to compute roots. And this is one of my favorite cartoons. This is Johannes Kepler trying to explain to his colleagues using the Newtonian principle. He says, so you see the orbit of a planet is elliptical, but he takes for granted that they don't know any of that stuff. So, the first guy is thinking, what's an orbit? The second guy is thinking, what's a planet? And the third guy is saying, what's elliptical? So, when you explain things, you can't take for granted what they know or don't know, and sometimes you have to start from first principles. If you're a Star Trek fan, this is one of my favorite episodes. On the holodeck, Data is playing poker with Einstein, Newton, and Stephen Hawking. Stephen Hawking actually made a cameo. That's really Stephen Hawking there in the wheelchair. And it's pretty funny because Data is trying to explain to Newton the laws of poker, and Newton kind of takes offense that Data is kind of condescending on him and says, don't condescend on, this, young man. I invented calculus, And they say, oh, okay, sorry, and they keep playing. It's pretty funny. How many actually see Star Trek episodes ever? Am I the only one in this room? Okay, a few. That's good. You learn a lot watching Star Trek, actually. Okay, so that's Newton, and he appears on the money, even today, on the British pound. Remember, the Brits never really converted to the euro. They kept the British pound. In fact, now they actually are exiting the European Union altogether, so they kind of were all obstinate to begin with about the euro, a little suspicious to begin with. But he appears on the money, as well he should, and on many stamps. So to give you an idea of all the stamps of the world, I just put down a few that have Newton on the stamp. And this is from very separate countries, right? Some of these countries are all over the planet, basically. And they all pay homage to Newton, and some of them even have some of his contributions on the stamps, right? Some of them show his telescope made of mirrors, not lenses, and some show, gravitational attraction and principle of orbits and so on. And these are all different countries, all paying homage to this one guy. It almost never happens that one person appears on everybody's country's stamps, not just a few countries, right? And I just collected a few. Republic of Congo, Grenada, Mongolia. Just every single country recognizes. And here's my favorite homage to Newton. Here he appears on the stamps of Korea. This is not South Korea. This is North Korea. North Korea doesn't even believe the rest of the world exists, if you follow the news. And yet they put Newton, an outsider, a foreigner, on their stamp, which tells you a great deal. They also kidnapped one of our students. How many know that? They're holding a prisoner. So I digress. That's besides the point. But they got this one right. So it's pretty amazing the contribution he made to the world, and still is, through his work and his theories and his physics and so on. So Euler. Euler, in the 1700s, basically invented graph theory. The famous bridges of Königsberg problem, basically the question was whether you can walk around the city of Königsberg, which is in old Prussia, now part of Russia, I guess. There were 7 bridges, and the river kind of split like that, and there was this island in the middle. And the question was, could you take a stroll and cross every bridge exactly once and end up where you started? And for centuries, nobody could figure out a way to do that, but they couldn't prove that you can't do it either. He came around, looked at this problem, and solved it after centuries of folklore debate about it. And the way he did this, he converted it to a graph. He basically said, these land masses are nodes, and these bridges are edges, and then he proved which kinds of graphs can have an Eulerian tour in them, and which kinds can't. Anybody know the actual characterization? What's a sufficient and necessary condition for a graph to have an Eulerian tour, a tour through the graph that covers every edge once and exactly once, no more, no less? Almost. He's saying an even number of bridges. It's a little bit more nuanced than that. It's almost there. Any other thoughts? When does a graph have an Euler tour? And by the way, if you speak up, you get points for bravery. No matter what you say, you're already a hero because you spoke. Everybody else is afraid and is quiet, and there's no win there. So, what do you say? Yeah, if all the nodes are of even degree, that'll work. And if you want an Eulerian path, not necessarily a tour, the number of nodes of odd degree may be at most 2. If you think about an odd degree, a path has to go in and out of that node. And it has to do it a certain number of times. Every time it goes in and out, adds 2 more. So the degrees better be mostly even, with the exception of 2 degrees, which may be odd. And then you have a path, not necessarily a tour. But that's okay. He discovered all this, and that solves a very, very general problem. And he also pioneered what we now call Euler's formula. Number of faces plus number of vertices is equal to number of edges plus 2 on any solid that you could construct, including a cube, a pyramid, a tetrahedron, a polyhedron, anything. in 3D. And in higher D, there's a generalization of this. And he discovered what we now call as Euler's number, the E, 2.71, the natural log base number. That's his discovery too. And probably what is considered one of the most, probably the most beautiful formula in all of mathematics. And that's saying a lot because there's a lot of beautiful formulas floating around math. But it's Euler's identity. E to the I pi plus 1 is equal to 0. Why is it so beautiful? Because it contains the 5 most famous constants in all of math. 1, 0, E, I, and pi. And they each appear exactly once. It also contains addition, multiplication, exponentiation, and equality once each. All the common operations. And this happens to be true, and it's very non-obvious. It's very non-obvious why, when you take E, which is an irrational number, and raise it to the power of the product of I times pi, why is it equal to minus 1? Think about it. I mean, you can prove it using, some series of steps. So it's not extremely hard to prove. It's just not obvious at all. In fact, it's not even obvious that e to the I pi will even be a real number, much less minus 1 exactly. Anyway, so one of the problems I asked you to prove last time is whether the set of exponentials, the set of irrational numbers is closed, or instead of rational numbers is closed, or irrational numbers is closed under exponentiation, and we said, are the set of complexes closed under exponentiation? If they are, what is I to the I, for example? Remember, how many remember that from last time? Still extra credit. The bounty is still open on that one, but it's related to this, so that's already a hint. And of course, he did lots of other contributions to many other things. He appears on the Swiss francs, and still does. The Swiss never changed to euros either, like the Brits. And Euler is right on the money there. And that's one of his treatises, among many. Again, from the 1700s, and typically written in Latin. His correspondence with some German princess, where he was tutoring her in mathematics by correspondence, because he wasn't right there to help her in person, became another treatise. And he invented whole new sets of mathematics to teach her, some stuff. And so even his letters, did math and did new math. So it's quite amazing. On stamps, sometimes you see the actual Euler formula or other formulas by him on the stamp. I think it's really cool when you see real mathematical formulas on the money or on the stamps. It's rare. Usually these things kind of condescend and geared towards the least common denominator of knowledge and interest. But whenever you see real formulas on stamps or money or other public instruments or documents, to me that's pretty impressive. The society that does that is typically ahead of those that don't, in terms of enlightenment and advancements and appreciation of science and knowledge in general. So in Geneva, there's a whole museum dedicated to Euler. I've been there. It's pretty cool. Here's a poster during the Euler celebration of, I guess 300-year celebration or 350 years. And so it's several of his formulas, but these constants, E, U, I, E, and R, spell Euler actually across this set of formulas, which he all invented and pioneered. This formula also appears in the episodes of The Simpsons. E to the I pi is equal to minus 1. You have to kind of look carefully, but they have mathematicians that inject mathematical humor into some episodes. And here's some books on graph theory. So it's very, very ubiquitous. It permeates all the other fields, graph theory and graphs. This is my top favorite few dozen books on it, and graph algorithms as well. You can have entire courses devoted to this. And here we'll just kind of touch on it tangentially and use graphs, but it's a field unto itself. People still write PhD theses on graphs and graph theory and graph algorithms and so on. There's entire conferences on graph theory, even to this day. So there's the Krakow Conference on Graph Theory. There's the International Conference on Graph Theory. This is last year's version. So entire conferences, multiple conferences, just on graph theory. That's how important graphs are. You can't underestimate the value, the importance, the significance, the contribution of graph theory to all the other fields. Every single field of scientific endeavor is relying on graphs in one way or another. Here's another graph theory conference, different than their other ones. Here's yet another one. So there's literally a dozen different theory. There's entire journals dedicated to graph theory and results about graphs, theorems, and graph algorithms. So Dijkstra and Prim's algorithms. How many heard of Dijkstra's algorithm, Prim's algorithm? Those are graph algorithms on graphs. So variations of these algorithms are studied in these conferences, all sorts of subtle versions and different scenarios and many other things about graphs. So I'm just showing you a few. And other. Applications of graphs. I mentioned there's lots of applications. Let's name a few applications. So geographical systems, GPS systems, they're modeled as graphs. Where's the graph in this? So here's like a Google Maps walking tour from Rice Hall, where we are now, to like the Rotunda. Where's the graph here? What is the graph here in this kind of application? Yeah. Yeah. So basically, the vertices are intersections, like street intersections or road intersections. The edges are actual segments of either you walk down a block or you walk from one street to the next or one intersection to the next. Those are the edges. So there's a kind of implicit graph there. And what algorithm runs inside Google Maps or your GPS system on your phone to come up with this tour? What do you think? What algorithm runs on this graph, roughly? Not necessarily exactly that, some variation of that algorithm, but speed limit, yeah. It's a weighted graph. Mm-hmm. And which algorithm, of the algorithms that we know and love and studied elsewhere, typically is applied to get you that? If you had to kind of name a classical algorithm on graphs, what would give you that shortest path, say, based on speed limits or total distance traveled or whatever optimization you want? Yeah, you're saying it. It's called Dijkstra's, but yeah, that's him. That's the guy, Edgar Dijkstra's. We already mentioned Dijkstra's algorithm a few minutes ago, but on this graph, you run Dijkstra's algorithm. That'll give you the shortest path, or the path with the least amount of time to arrival based on speed limits, and the edge weights are the speed limits, or they're the distances traveled, depending on if you want to minimize the time or the distance, or some combination of the two. Lots of other applications. Subway maps. If you go to New York or Paris, you see, or London, you see this funky-looking maps. They're basically graphs, right? The edges are segments of between stations, and the nodes are the stations, right? And the edges are the actual train tracks. So whenever you see a subway map, you realize it's a graph. And again, you can use Dijkstra's algorithm or variations of it to figure out paths and so on. Computer networks are graphs, like the internet or subnetworks or the web. Here's a map of the internet, very, very complex, many billions of nodes. The vertices are routers or PCs or computers. The edges are fiber optic links or Ethernet links or whatever the links are. Again, Dijkstra's algorithm could be used, or many other routing algorithms could be used to route packets around and send things around the internet. Again, all due to Euler and his graph theory. The World Wide Web is one big graph. Here, it's a logical graph, not necessarily a physical graph. The nodes are what and the edges are what on the web? You have websites. Where's the graph there? Yeah. Yeah, web pages are nodes, and the edges are, what are the edges? Hyperlinks, links, URLs, right? So the whole web is one giant graph with trillions of nodes by now. But once you present something as a graph, you can apply all the classical graph algorithms to it, like Prim and Kruskal and Dijkstra and many, many others. There's thousands of famous graph algorithms that do all sorts of things, including routing and shortest paths and navigation and connectivity. Social networks are graphs. In a social network, what are the edges? What are the nodes? Social networks like Facebook. What are the nodes in a social network? You are. Each one of you is a node. The people are the nodes. The links are what? Friends, or friendships or friend requests or whatever you want to call them. It's probably a bad name to call them friends, because when I used to be on Facebook, whenever somebody deleted a link to a friend, they call it unfriending, and that has a very negative connotation. It's not unfriending; it's removal of a link from a graph. And there's no derogatory, kind of hostile notion to it. Except people will get insulted and even upset, And so whenever after I was seeing too much of that, I just decided, forget Facebook. I'll just buy some stock on the IPO. And I did very well. So keep using it, all of you. It paid for my Tesla Model S. Thank you very much. So that's what social networks are. Graph databases. So you can have vertices being records, edges being relations in a relational database. Many, many applications. The electrical grids, the vertices are stations, the edges are cables or connectivity of wires, electrical wires. And here's the main backbone of the electrical grid of the United States shown pictorially. There's many other details to it that are smaller, but this is like the backbone, the big edges. Chips, integrated circuits. What are the edges? What are the links? Or what are the edges? What are the nodes in a VLSI circuit? Graph model of a VLSI circuit. The nodes are what? Not mysterious. Electrical components like transistors or ALUs or memory locations. The links are what? Yeah, what are they called? One word starts with a W. You want to buy a vowel? Wires. Yeah, but you're right. That's what they are. Wires. And so this shows you ubiquity of graphs. It's hard to underestimate. Their ubiquity and their value and what you can do with them. In a building design like this one, your HVAC system or any other connectivity system, again, the vertices are connectors and the edges are ducts or wires or cables or Ethernet links or whatever it is going on in the building. Semantic nets, same thing. Vertices are objects, edges are relations. Even more importantly to this course, we're going to talk about finite automata, and those are graphs too. So we'll talk a lot about finite automata and Turing machines. Each one of those is a graph. And we have the vertices being states and the edges being transitions between states. Now these graphs depict computations. And as the computation changes and states change to other states, and the thing is now computing something, and we'll talk a lot about, you see a lot of these diagrams, but again, they're all graphs. I want to show you the full scope of how graphs permeate every aspect of human endeavor and engineering and science. And all the computations that we'll see in this course are also depicted as graphs, and sometimes very, very explicitly, with nodes being circled and edges being. So you already saw some of it last week when Nathan gave the lecture. We'll see a lot more of this coming up as well. Even you represent time and space complexity classes like the Chomsky hierarchy, you can present complexity classes as nodes and their containment relationship, subset containment relationship as edges. So even that, at a high level, is represented as a graph or as a Venn diagram alternatively, but can also be represented as a graph. So in terms of map coloring, you can have regions associated with nodes, and graphs can show you adjacency of regions. So map coloring and coloring problems, we'll talk about those. We'll talk about NP-completeness more. Vertices represent countries, edges represent neighbors. Countries are neighbors that have an edge between them. Countries that don't have an edge between them are not neighbors, are not immediate geographical neighbors. Lots and lots of other applications, including Erdos numbers, is more on the humorous side. Kevin Bacon numbers. How many are Kevin Bacon numbers? That's a big graph also. With Kevin Bacon, the center of the universe. When he first heard about this in the 90s, he was very insulted. He thought it was a big joke, and it kind of was, actually. But then he realized that being named, this Kevin Bacon number after him makes him more popular and more ubiquitous, not less. So in show business, any attention is good attention, even if it's not so good. So so the vertices are like authors, and edges are co-authors in Erdos numbers. And of course, Kevin Bacon numbers is a takeoff on Erdos number. How many heard of Erdos numbers? Erdos is a famous mathematician who passed away, in the late 90s. One of the probably best published mathematician on the planet. He had over almost 2,000 papers or something like that. And anybody who published with him directly was Erdos number 1. Anybody who published with somebody who published with him directly but didn't publish with him directly was Erdos number 2, and so on. So the Kevin numbers were kind of a takeoff on that. Okay, Carl Friedrich Gauss, we already mentioned him when he was 7 years old. He invented this formula for sum of integers, but he did many, many other things. It was called the Prince of Mathematics, and very rightly so. He invented the fundamental theorem of algebra. What's the fundamental theorem of algebra say, by the way? So it's not that complicated, but what's the statement of the fundamental theorem of algebra? let me ask you a leading question. What's the fundamental theorem of arithmetic? The fundamental theorem of arithmetic says what? Not that. He says 1 plus 1 is 2. It's not that far off. I mean, it is something very simple. Any two numbers can add up to another. Again, it's probably a consequence of it or related to it, but it says something a little bit more than that. The fundamental theorem of arithmetic, yeah. Yes, every integer can be factored into prime numbers in a unique way. Now, there could be several multiple primes all the same, but it's still a unique factorization into primes. So what's the fundamental theorem of algebra then? Yeah, every polynomial of degree n has n roots. Now, some of these roots could be the same as the others, but every polynomial of degree n has n roots. What's the fundamental theorem of calculus? Every field has its own fundamental theorem. I'll let you think about that. Any questions about anything? So remember, 2 things are due every Monday. You have a lot of leeway, but submit them. Don't fall behind. All right? See you next time.